Welcome to the Explainer. Today, we're going to roll up our sleeves and tackle a classic physics problem from the legendary Irodov collection. We're looking at problem 1.19 from kinematics, and let me tell you, it's a fantastic workout for our physics brain. Okay, let's break down our challenge. On the surface, it looks pretty straightforward, right? A point moves in a semicircle. But this problem is so clever because it's specifically designed to see if we really understand the difference between speed and velocity, distance and displacement. The details here are absolutely everything. So first things first, let's get organized. What do we know for sure? We've got the radius, r, at 160 centimeters. We know the whole thing took 10 seconds. We know the path is exactly half a circle. And then there's this little gem right here, which is going to be super important later. The point moved with constant tangential acceleration. Let's pin that for later. Here's how we're going to attack this. First, we'll calculate what the problem calls mean velocity, which is really the average speed. Then we'll dive into that critical difference between speed and velocity. After that, we'll get into the trickiest part, the average acceleration, and then we'll wrap it all up. Sound good? Let's jump in. All right, let's get to our first task. Part A asks for the mean velocity. Now, in today's physics language, we'd almost always call this average speed because it's asking about the total length of the path. So let's figure that out first. So the whole idea of average speed is that it's all about the total ground you covered. Think of it like the odometer in your car. It doesn't care if you drove in circles. It just adds up every single meter you traveled. It's a scalar, so direction doesn't matter one bit. Our point traveled along a semicircle, so the distance it covered is just half the circumference of a full circle. The math is nice and simple. It's just pi times the radius, r. Now we just plug in the numbers we were given. We've got pi times 160 centimeters, and we divide all that by the 10 seconds it took. Punch that into a calculator, and we get an average speed of about 50 centimeters per second. Easy enough. That's part A done and dusted. Okay, now for part B. It asks for the modulus of the mean velocity vector. Now, that sounds an awful lot like what we just did, but this is where being a careful physicist really pays off. It's asking a completely different question. And this right here is the classic kinematics question, isn't it? Is the average speed the same as the magnitude of the average velocity? The answer is a huge, definite no. Well, not unless you're moving in a perfectly straight line without ever turning back. Understanding why is one of the biggest keys to getting motion problems right. I love this comparison because it makes it so clear. Distance, on the left, is the long winding road you actually drove. It's the total path. But displacement, that's the shortcut home. It's the straight line vector, as the crow flies, from your starting point to your ending point. So to find average velocity, we have to completely ignore the scenic route the point took. We only care about one thing, that straight line displacement vector. We find its length, and we divide that by the total time. So let's picture our setup again. The point started on one side of a circle, and it ended up directly on the opposite side. The straight line distance between those 2 points, well, that's just the diameter of the circle, which is simply 2 times the radius. And check this out. This is the perfect illustration of why this matters. The displacement is 2 times 160, so 320 centimeters. Divide that by our 10 seconds, and the magnitude of the average velocity is only 32 centimeters per second. Look at that. It's way less than the 50 centimeters per second average speed, and it's all because the path wasn't a straight line. All right, let's move on to the grand finale, part C. This is definitely the trickiest bit, finding the average acceleration. To do this, we need to think about how the velocity vector, not just the speed, changes from the very beginning to the very end. This is so important. Average acceleration isn't just about the change in speed, it's about the total change in the velocity vector. That means final velocity minus initial velocity. And since velocity includes direction, you can have acceleration even if your speed is constant, just by turning a corner. In our problem, both the speed and the direction are changing. Now, this might look a little intense, but trust me, we have a clear step-by-step plan. We're going to use the clues we have to connect everything together, find the change in the velocity vector, get its magnitude, and then just divide by time. Okay, remember that little phrase I told you to pin from the beginning? Constant tangential acceleration? Well, here's where it becomes our secret weapon. Whenever you have constant acceleration along a path, there's a super useful shortcut. The average speed is just the simple average of the starting speed and the ending speed. So if we just rearrange that little formula, we find that the initial speed plus the final speed has to equal 2 times the average speed. We already found the average speed was 50 centimeters per second, so their sum has to be 100 centimeters per second. We don't know what they are individually, but we know what they add up to. Now for the vector part, which is really the heart of this problem. At the beginning of the semicircle, the velocity vector is pointing one way, let's say straight up. By the end, it's going the other way, straight down. The change in velocity is the final vector minus the initial one. And here's the trick. Subtracting a vector is the same as flipping it 180 degrees and adding it. So our down vector minus our up vector is really the down vector plus another down vector. The magnitude of that change is just the sum of their individual speeds. And just like that, we have everything we need. The magnitude of the average acceleration is the magnitude of the velocity change, which we just found is 100 centimeters per second, divided by our total time of 10 seconds, and that gives us our final answer, 10 centimeters per second squared. Phew, okay, let's take a step back and pull this all together. A quick summary is the best way to make sure these concepts really stick. This table just lays it all out so perfectly. We calculated 3 very different things. The average speed, 50 centimeters per second, tells us how fast the point was actually scurrying along its curved path. The magnitude of the average velocity, 32 centimeters per second, tells us its effective speed in a straight line from start to finish. And that average acceleration, 10 centimeters per second squared, tells us, on average, how much the velocity vector was changing every single second. And that really leaves us with this final thought. To tell the full story of any motion, you can't just pick one. You need both, distance and displacement. One tells you about the journey and the effort it took, and the other tells you about the destination and where you ended up. You need both to see the complete picture.